schedule, and then after going over class schedule, we'll get to today's lesson. Today's lesson is, like I said, the least mathematical, but there will be one slide where you will need your calculator for today's lesson, but it will have to do with what we've already done, which is pH calculations. I wanted to give you the rest of this unit schedule so you know what's going on the next couple of weeks. I've tried to keep in mind all of the Cambridge exams that are coming up when formulating this schedule. I know that this is primarily a 10th grade class as well. I know when we get to that final unit, it's going to get a little bit grainy. There will be several days that you are missing this class completely due to Cambridge testing. And so I will consider that. There's only after this unit 4 more lessons to get through until we're done with the year. So we will be able to cover that and be able to have your final test for sure. Because in that last unit, unfortunately, there are no labs in the final unit. It goes back to like drawing with structures. So it's a little bit more of a brain break type of, it's still really, really important topics, but it doesn't require the hefty math that you're currently doing. So we're going to go ahead and go over, like I said, class schedule first. Today, we are doing Unit 7, Lesson 3. Some of what we do today will be review and some will be new. We're going to be going over acid-base theory today. There are 3 theories of acids and bases. There's 2 we're going to go over. 1 we've already went over. The second, Cambridge likes to test. It's an important one, so we'll be going over the second theory today, which is also in the class. And then the third theory of acids and bases, I don't cover because Cambridge doesn't cover it, but there is another theory that exists out there. If you're interested, you can ask during tutoring. But you wouldn't really need it until a deep dive study into organic chemistry. And so today we'll be covering the acid-base theories needed to progress through the class. And next class, that's Friday, right? Friday. This is my marathon week, by the way. There's a lab set up every single day for our class, so I'm staying till like 5 or 6 p.m. every single day, and I'm here for 4 hours on Saturday. So I'm like, we're on Wednesday, right? So Friday, we're going to be doing what's probably the most difficult lesson of the unit. I'm going to be honest with you. It's the most intense math lesson. It's the last lesson, but it's the most intense. So mentally prepare yourself for it. You'll know why when I say the topic title. It's called Solution Stoichiometry. Solution. So that's Unit 7, Lesson 4. Stoichiometry. When I say stoichiometry, what should trigger in your mind is that means we're going back to balanced chemical equations and converting between moles and moles or grams and grams. But now we're going to incorporate the concept of molarity into the mix. So that's why I said it's more difficult because it'll be several steps to solve questions, up to 3 steps. So we'll be going over exactly how to do that and acid-base titration. The theory of acid-base titration we'll be doing on Friday. Leading us into next week, Tuesday, we'll do review and titration lab. That's a really important lab that you do. It's our last lab of the school year, and it's actually the first type of lab you would see in an AICE course, where you do a reaction between an acid and a base. It's called an acid-base titration. And so you'll be getting comfortable with that next week. No more after next week. The last unit, like I said, does not really have. I said it's good news and bad news. It's a short unit, but the reason this unit's been extended is because we've been having so many labs, if that makes sense. I could have tested you this week. You could have finished and like marathon through and then went through it. But it's better to give you the experience of having those lab skills. That's why we've slowed down the pace a bit. That's why you've been practicing a lot. And so that's Tuesday, is a review/titration lab. Next week, Thursday, is a full review day for those of you that are here. / extra credit given. Extra credit for exam. The reason why that's going to be review / extra credit given is because for many of you next Thursday, you have a test. I believe it's psychology and English general paper. Are those the 2 for next Thursday? So many of you will be testing in the morning that day. I'm not sure if I'm proctoring or not, so I'm going to give you, regardless of if you're here or not, an extra credit practice to work through to help you to practice for the exam. because the exam for our Unit 7 is going to be, and I believe I had told you this before, but I'm going to tell you now, it's on April 29th, which is the Monday afterwards. So it's about a week and a half from now. Monday, 0429, there's no testing that day. There's no testing for a few days each direction. So Monday, 0429, that's going to be our Unit 7 test. Like always, we will have a time to review. You won't come into the class and take the test immediately. You'll have a little bit more time to practice, do some practice questions, and then we'll take the test to give you about an hour and 15 minutes, most likely, to take the actual test. And we'll talk more about exactly what's on the test, but it's pretty much these 4 lessons will be all the material on the test. So that's the schedule. That's what we're following. If you do not have tests on next Thursday, I do want to remind you that is Take Your Child to Work Day. I do support that. So if you are going to take your child to work day, just let me know that that's what you're doing that day if you are not testing that day. Yes. Cool. I support that. I'll make sure you have the extra credit packet so that you could do it to turn in on the day of the test. So I'll be giving that out next week, most likely on the day of the titration lab, so that those students that are missing on Thursday still have that opportunity. All right, sound good? All right, so this week, rest of the week, we've got 2 lessons to get through. We'll be done with this unit after this week. Then next week is pretty much all review and lab, and then the week after, we'll take the Unit 7 test. And then we only have like 4 lessons to go after that until we're done with the school year. So, oh, don't worry. You'll be in most likely the media center for like a week because we'll be using this place to set up. So you'll have like an end of year thing to do, and you won't be in this classroom for like after the testing because we'll be testing for labs in here. So it's like that. No.
I still remember vividly how last year there was like this fiery smell coming from this end of the hallway.
We don't want another gas.
Don't start rumors. We will be using the Bunsen burners. We have to use the Bunsen burners. It's part of our exam. We do it every year. It's not a problem. Anyway, all right. So we're going to go ahead and get started. All right, Unit 7, Lesson 3. Today we're going to be going over theories of what makes an acid, and what makes a base a base. We actually already, because I wanted to kind of bring this up in advance before we actually got to the unit on acid and bases, so I did a lesson back in chemical reactions where we talked about acid bases a little bit. And do you remember what the initial definition of an acid was? What's an acid in its most simple definition? Right. So the simplest definition of an acid, the first working operational definition that we have, is that it's a substance that has H plus, right? That has H plus. And so if we put it in water, it's going to dissociate, and we can detect that with our 3 different methods we learned last class: indicator, litmus paper, or pH meter. If it's got H plus, it can be detected. And so that is our simple definition of an acid. What was our most simple definition of a base? Like the most simple definition. The one we've been operating off of so far. pH scale has to do with it. What is our most simple definition of a base? Right, so it's going to have that polyatomic ion hydroxide in it, right? OH minus in order for it to be a base. Or when it's placed in water, actually, it releases OH minus. That's the first working theory. So the first working theory was the substance has OH minus, right? Those are our basic definitions, but it doesn't cover everything. We have an issue. We did a lab last class. And that's why I have my gloves ready to remind you of something. We did a lab last class, which was only 2 days ago. And you had a solution of ammonia. And it was labeled, maybe, NH3. Ammonia is NH3. And so I have that here. And so ammonia is NH3. Do you know what ammonia is used for? Anybody know?
Fertilizer.
It's used in fertilizer, yeah. What else? No. That's CHCl3. It is not chloroform. It is used as a cleaner, actually. You can buy it in the cleaning aisle in Publix. You could buy ammonia there. So it's actually used as a cleaner. I would not use it as a cleaner because I don't like the smell of it. But I guess some people do. Must. However, it is actually dangerous if you mix it with the wrong thing. It can produce something very toxic that can cause you to pass out and possibly die. And so that's why they tell you not to mix your kitchen cleaners together. Have you ever heard that?
Yeah.
Never mix your kitchen cleaners together because if ammonia mixes with the wrong thing,
Is it like yellow gas?
right?
What is that from?
It's the thing that Germans use in
Yeah, it is.
Right. And I have brought it up before, I'll probably bring it up at some point, that it actually happened not too long ago. There was somebody who was cleaning up in a Buffalo Wild Wings, not in Florida, it was in a different state, but they didn't realize that they ended up mixing those two chemicals. There was something that was already on the surface that they mixed with ammonia, and then they ended up dying, and several people got taken out like in an ambulance because they mixed the wrong two things together. So, just a brief aside. Do not mix your kitchen cleaners together. And then that's the same thing. If you're in a lab, you should always ask permission, because I know what everything is, before you start mixing random things together. I told you in the last lab that it was fine because I ensured that everything I put out was something that could be mixed together. But you have to double check with me beforehand before doing anything that's, a different mixture than what you're being told. Okay? All right, so talking about ammonia, now we're talking about this NH3 substance. I have my red litmus paper. I put it into ammonia. What color does it turn? It turned blue. Which means what about ammonia?
Base.
I don't know about you, but I don't see OH minus, right? I don't see OH minus. So how do that be base? So we're gonna figure that out today. We're gonna figure it out today. In today's lesson, why is NH3 a base? You are on the right track, and I will explain it fully shortly. There is something that happens, and it would have to do with the Lewis structure if you really understand what's going on, and that's an ACE level idea. What? There's something in that Lewis structure that's going to allow it to do something to make it a basic solution with water. Why base? Stay tuned. Because the first operational theory doesn't work for ammonia, which is why we need theory number 2, which is the one that I said Cambridge emphasizes on. It's going to be called the Bronsted-Lowry theory, but we'll get to it shortly. So I just wanted to bring that as like an idea that we're going to start off with. All right, couple of things. I'm going to go back old school and remind you, you got to know your group charges. I say this 100 times over the school year. Write this if you need to remind yourself because you're going to be doing something with the group charges real shortly. Every element, when it ionizes in group 1, has what charge? Plus 1. The reason I do this is if you're in the ACE class, it's expected you know this. Like, that you could just pull that off the top of your head. That's why in pre-ACE I tell you 100 times that these are what the group charges are. Group 2 is plus 2. Group 13 is plus 3. 14 is plus 4 or minus 4.
Slash, yeah.
Then we switch from the metals to the non-metals, which is why the charges go from losing electrons to gaining electrons. And we have -3, -2, -1. These group ionic charges must be memorized because they can come up at any time. You're going to see them real shortly come up in a question. So you just need to write those to remind yourself. They're up there. You will have a question where you have to use the group ionic charges in a little while. And then later on in this lesson too. All right, so the first things first. Talking about acids and bases that you should know. I'm actually pretty sure that I reviewed these with you 2 months ago when I went over the first acid-base lesson, but I'm just going to do it again because I want to make sure that you really know these. There are some acids you should memorize by heart, their names and their formulas. These are the 5 that Cambridge actually requires you to know at an ACE level, so those are the 5 that I'm asking for you to know. You should know that hydrochloric acid is HCl. Go ahead and underline the H that makes it an acid. So we should do that just for our future benefit. Nitric acid is HNO3, and you can see the chlorine. Nitric comes from nitrate. Sulfuric comes from sulfate. Acetic. Where do you think the acidic hydrogen is in acetic acid? It's only the last one. That's why it's separated out. It's the one that's next to the super electronegative oxygen. Just that is the acidic hydrogen. And then phosphoric acid is these 3. You can actually, for any polyatomic ion, predict its acid formula. How can you do that? Let's take a look at sulfate. SO4 minus 2. How can we predict the formula of its acid? Just knowing the polyatomic ion. If I know that I'm putting H that has to have a +1 charge with sulfate that has a -2 charge, then if I use the technique that we learned all the way back in Unit 3 of crisscrossing to make the charges equivalent, you would get the same thing it says there, H2SO4. These are just the combinations of putting H plus together with each of the polyatomic ions that you see. Because NO3 is -1, there's only 1 hydrogen. Because PO4 has a 3- charge, there's 3 hydrogens, 3 H pluses to counter it. And so this is the first thing I wanted to point out is where is the acid in each of these 5 acids you need to know. I do want to remind you of the purpose of each of these acids. HCl has a few purposes. One of them is actually it's your gastric acid, is hydrochloric acid that's in your stomach. Gastric acid is HCl. And what is the purpose of your stomach acid?
Dissolve food into.
So it actually hydrolyzes, it breaks apart the bonds, the chemical bonds in your food to make large molecules into smaller molecules that could be digested quickly. So that's the purpose of the acid in your stomach. It's also used as pool cleaner. It has a name called muriatic acid if you buy it as pool cleaner. And so I have a friend who's a pool cleaner and he uses it all the time. And he gets it on himself. I'm like, does it burn? He's like, yeah, but it's okay.
Yeah, it's only a light burn.
I'm like, okay.
It's only gonna
It's got like burns on him. Like, okay, if you want to live your life that way.
What did that cost?
Maybe skin issues for sure. That's what he says. Nitric acid, HNO3. This acid can be used for a couple of different things. It could be used as a fertilizer, but it could also be used as an explosive, actually. And so, for example, TNT, trinitrotoluene, uses nitric acid in the process of creation of TNT. And so it can be used for explosives. Sulfuric acid, that is battery acid. So if you've ever had to change a battery in a car, you've seen your a family member change a battery in the car, and they have to be real careful about it, is because of the sulfuric acid. It's a very dangerous acid. Yes, go ahead. Acetic acid is the acid. Have you ever had salt and vinegar potato chips before?
Yeah.
That's the acid that's in that. Vinegar acid is acetic acid. It does not make me hungry. And then phosphoric acid is the acid that's actually, if you've ever had Coca-Cola before, that's the acid that's in Coca-Cola. You can look at the back of the ingredients list and it's there. But these are the 5 that Cambridge wants you to be aware of. Are there more? Absolutely. There's a lot of other acids that exist, but these are the 5 that have the most common usages, so that's why those are the only ones you need to go ahead and memorize. If you had to memorize more, you have to memorize a whole set of rules. Remember how we had rules for covalent compounds and ionic compounds? There's a whole set of rules for acids as well. I don't teach it because you don't need it. This was our first theory. This was the one that I presented already, right?
Yeah.
The Arrhenius theory is a compound that dissociates in water and yields H+. You should circle the word dissociates. Do you remember what that means? Right. So this is something that separates in water and it gives off H+. Yield means a product is going to be H+. Yields means product. And then the same thing for base, except it dissociates and yields OH minus. That's our first definition of what makes an acid and what makes a base a base. It's the one we've been working off of. Just to show you the dissociation reactions, you are gonna have a couple to do yourself in just a moment. But just to remind you, what is the dissociation of H? Let's do HBr. How would you do that? Dissociate HBr. What would that become?
H
H
plus
plus, because we're talking about how does this break apart in water. H plus is the one product. What's the other one?
Br.
Br with what charge? If H has a positive charge and the whole thing is neutral, what is the charge of bromine gotta be? Negative 1, right? Or just minus, because it's a 1, so you don't have to write 1. So it would be plus 1, minus 1 if you want to write the numbers there. And then what state is it? Because they're still dissolved in water, it would be AQ. And this would be detected by your pH meter, pH plus 1. And what if I had a base, like LiOH? How would that dissociate? What does this dissociation look like? Perfect. And H minus 1, because it's got to be the opposite charge in hydroxide. It's always -1. And then you write your little AQs there. So that's what the general dissociation for an acid and the general dissociation for a base. You're going to have a question to do real shortly. It's on the next slide. Where I'm going to ask you to try to do 3 dissociations of your own. If you get them right in the next 5 minutes, I'll give you a stamp. Right here. Write the dissociation. Oh, I already did HBr. Well, that's great. You only got 2 more to do. Well, you got to get all 3 though. So your turn. See if you can do each of these dissociations. Once you have all 3, raise your hand. I'm going to give you till about 8:32 to do this. And I'll check, and if you don't have it right, I'll tell you what to correct. I noticed that I did get kicked out of the meeting, so I'll go ahead and I'll put myself back into the meeting while I'm waiting. So one of the practice questions, this is your turn for your first opportunity for a chance today. What happened? I feel like the internet's always a little temperamental in the morning.
It's its own call.
I can't. Where do I forward it in? Where do I forward it in? Go ahead. So this is your turn. Take till 8:32. You've got about 4 minutes now. Try to see if you can do these 3 dissociations. Have me check it. I'll let you know if you're right and stamp it. And if you need to fix something, I'll tell you what to fix. Thank you. The only thing here is that there's 2 hydrogens, so you have to balance it basically. And then here, the balance. Very nice. All right, once you have it, let me know. If you get it by 8:32, I'll go ahead and give you a stamp for your notes. Got it? We're on slide 5. Slide 5. Ready? Should stay. Alright, so then another minute. Remember to have me check and I'll let you know if it's correct or if you need to fix something. Yes, ready? You may want to pull out your polyatomic ion sheet. Okay, so I'm gonna go ahead and give you the answers if you weren't able to get it. It is 832. The first one I already did, so everybody should have that one. H plus Br minus. Then I noticed a lot of you did get confused with the other two because of the amounts. If you've got H2SO4, the idea is that when this dissociates, it breaks apart into two H pluses because there's two H pluses in this chemical formula. That's how H plus and SO4 minus 2 ends up combining if you think about the ions that combine to make this. And so this should be H plus SO4 minus 2, where polyatomic ions always stay together. They never get broken apart. So you may want to write that note. If it's a polyatomic ion, which I do have the list up here, if it's polyatomic ion, it stays together. But if you see a lot of oxygens, that's a clue, it's a polyatomic ion. And so how many H pluses? This isn't balanced yet. What do I put in front of H plus? 2. And so it's important to note that you put the 2 in front, not in the subscript, because that's something completely different and actually something that doesn't really exist. And then finally, I put the state, AQ, AQ. Just to explain what does this mean, I've shown this before when I taught this a couple months ago, but what this means is that for every one H2SO4, in water, you actually have 2 H pluses and 1 SO4 minus 2. These are the ions that you actually have in water that would be detected when it dissociates, when it breaks apart. This is what you have. BaOH2. What about that one? What would that break apart to become? Your positive ion is barium. What is its charge? Comes from over here, +2. And then for hydroxide, you have to remember that stays together. It's in parentheses, that's a clue to let you know that stays together. It's also base, right? OH minus. And then what do you do with the 2 on the outside of the parentheses? Where does that go? It goes in front to say I have 2 hydroxides. This matters. It's going to matter to the math we'll do later on. That's why I'm bringing it up. And then we write that this is again dissolved in water. So this is the first theory, which is the Arrhenius theory, which is the one that we have looked at before. I'm just bringing it back to your memory. So will there be some chemical reactions in this unit? Yes. They're not really too different from what we've seen in the past, but there will be some chemical reactions to work through in this unit. And I told you the last lesson is stoichiometry, which involves exactly chemical reactions. Ready to continue? Or need a little bit more? We're good? Checking to make sure everybody's done writing. Go. We're good? Okay. So next thing. This is something that I might have mentioned before, but I wanted to make sure that I do mention this before we get to the second theory. I believe that I gave you some questions in either last class, I think it was last class, before the lab, where they mentioned H3O plus and to like find the pH if they gave you a concentration of H3O plus. And I wanted to put this out here. You should note, and I'm going to explain a little bit more of why when we get into the second theory, that H3O plus is acid in solution. These two are the same thing. So whenever you see H plus, you could see instead H3O plus. What this means is that in water, water always accepts the H plus from the acid and becomes the acid. Water becomes the acid in water. So when acid gives away its H plus to water, water becomes the acid. So acid in water is H3O plus. And so you may want to write that little note for yourself. Which means that depending on your resource, I have so far, I said that pH was the negative log of H plus. But it can also be written that pH is the negative log of H3O plus. So depending on what you're reading up, what Google, what YouTube video you're watching, they'll use one of those two formulas. You just need to know that these two are actually the same as each other. So if you're looking for the negative log of the concentration of acid, we could call that H plus, or we could call that H3O plus. Because water, when combined with acid, will always take H plus.
It's the ghost. The ghost of CIE wants to go right
I mean, they use those stairs there to walk up to the roof, so
person who
hopefully
died.
somebody didn't fall the stairs.
Oh, that might have.
Yes, like the ladder. There's a ladder right outside.
I've seen that. I've seen one of them fall off, and the two other guys that's probably like back off.
I don't have my backpack, so no. I think Damien, he left a little while ago. So, wait a little while. Good to continue?
Outside. Yeah.
That's gonna be froze.
Like, how do you get outside though? I don't know, but there's like stairs right outside the window. I hope that wasn't there. All right, the next thing we need to discuss is there are actually 3 types of acids that you need to be aware about by name. And so Cambridge does use this terminology in questions, so that's why I wanted to bring it up. You could classify an acid as monoprotic, diprotic, or triprotic. So we're going to break down that word. What does that actually mean? First thing is these prefixes you should recognize. Circle them. Mono,
1,
1. Di,
2,
2. Tri,
3.
3. Okay. First part. What does protic mean? Underline the prot. Where have you heard of proton? Okay, let's talk. H, and I think I brought this up before, but I'm going to bring it up again. What's H plus 1? Let's go back to its subatomic particles. Protons, neutrons, electrons. The mass number of 99% of hydrogen is 1. And the atomic number is 1. How many protons, neutrons, and electrons are in H plus? That's it, right? How many protons, how many electrons, and how many neutrons? Protons, how do I figure it out? This goes all the way back to Unit 1, right? We learned this, I think, in Unit 1, very first study. How do I find the amount of protons? I look for the atomic number, the whole number, right? Which is the number what?
It's been so long.
It's been so long, right? 1. Hydrogen has 1 proton, agree?
Yes.
Okay,
Looks like
positive 1 means what's happening with the electrons. Are they being given or taken away? So you start with 1 proton and 1 electron, but you're taking away 1 electron. So how many electrons does H plus 1 have? In a neutral atom, you would have the same amount of protons and electrons, 1 of each.
Yeah.
What does plus 1 mean?
That there's one.
That it lost an electron. It started with 1. If it lost one electron, how many electrons does acid have? 0. Right? Because you've got this plus 1. You don't have a negative countering it. That's why it's plus 1. And how many neutrons does an acid have? The mass number minus the atomic number, right? Because remember, the protons plus the neutrons equal the mass number. Whereas this is just the protons. Going back all the way. Bring it back. How many neutrons does acid have? And acid is a proton, which is why all acid solutions and advanced scientists in advanced scientific papers will call acidic solutions protic solutions. That's what they'll call it because it's just a proton. Does that make sense? So protic means proton equals H plus. You can do that meme where like the brain just expands. Like
You can't have like a proton by itself.
H plus is a proton, isn't it? Like running around an aqueous solution, corroding whatever it can. That's what H plus is. Think about it. We know acids are corrosive. We know they're dangerous. They're literally single protons in your solution running around.
I would.
What?
I would.
So just to give you an idea, so now we understand the words, right? Monoprotic means 1H plus. Diprotic means 2H pluses. And triprotic means 3H pluses. Got it? How many acidic hydrogens are in your acid? And so you can look at the chemical formula of an acid and figure this out hopefully really quickly. I'll give you about 20 seconds if you were writing this down. Monoprotic, 1H plus. Diprotic, 2H plus. Triprotic, 3H plus. It's just being aware of the terminology. It is assumed in the AICE class that you know this terminology. That's why we go slow and explain it here.
They assume a lot of stuff.
That would assume you have a polyatomic ion that has a negative 4 charge. Right? Then you will have a tetraprotic, I would believe.
Sextoprotic.
Hexaprotic.
Dodecatoprotic.
All right. Determine if the following acids are monoprotic, diprotic, or triprotic. Look at the first one. It should be something, hopefully, that you can pick up quickly. H3PO4.
Sure.
Triprotic. If it was to dissociate, it would break off to make 3H pluses, right? HI. Hydroiodic acid is what it's called, but is it what type?
Mono.
Monoprotic. Monoprotic. And then H2SO4.
Diprotic.
Triprotic. That means that every one H2SO4 will actually break up 2H pluses. The reason I'm not only to talk about Cambridge tests, assuming that you know this, but also we're going to use this for some of the math we do later on. That's why I'm bringing it up. So could you be asked a question this simple in the multiple choice? Try to not only give you math questions, but there will be a lot of math questions in this unit because you can see that that's most of what we've been doing. This lesson is where most of the non-math questions are at. All right, we are ready for the second theory. The first theory, remember, was an acid, when it dissociates in water, it gives off H+. When a base dissociates in water, it gives off OH-. That was the first operational theory. But didn't really quite explain why ammonia is a base and is turning basic, right, in water. So now we're going to get to why. And so we've also got those little cards. I'm going to explain what you're going to do with those very shortly. So Bronsted-Lowry theory, the name comes from the name of the scientist, as often theories do. If you come up with a theory that gets approved, you get possibly a Nobel Prize. You can have your own theory named after you that's taught in 40, 50 years in classrooms. But Bronsted-Lowry theory is used throughout all levels of chemistry because it explains more compounds that are acids and bases than what the Arrhenius theory does. And so in the Bronsted-Lowry theory, acids are defined as any substance that donates H+, gives away H plus. So really when we talk about Bronsted-Lowry theory, we're talking about the action of an acid and a base. Meaning, what does an acid do and what does a base do? Like, what is the actual action, the chemical action that's happening? So it's like the verb. So substance that gives away H plus. In the business of giving away H plus. And then a base is an H plus acceptor. What does that mean? Something that will take the H plus. From the acid. This is actually very similar to another definition you heard a couple of months ago. You remember redox? Do you remember redox? It's been a while, but we learned back in the day there was something called redox. And in a redox reaction, whatever was being oxidized would give away electrons. And whatever's reduced would be receiving. Take a look at how close acid-base theory is to redox. Acid-base. If you really think about it, what's going on here? What's an acid is giving away what? What is H plus also that I just taught you? What subatomic particle is acid?
Proton.
It's literally just like redox, except instead of electrons we're talking about protons, acid-base reactions. They're actually extremely similar processes. Which is why in the Cambridge course, when you have what's called a titration, which you'll learn next class and next week when we do one, there's two types that exist, acid-base titrations and redox titrations, because you could either be transferring protons or you could be transferring electrons. And so the processes are actually quite similar to each other. So you may want to write this down. And so acids give away H plus and bases receive H plus. All right, so I'm gonna, if you have one of those red cards, you are the acting acid right now. Go ahead and give someone that doesn't have a red card your red card. Decide who. Go all around the room. Someone who doesn't have a red card. Make them an acid.
You're not so you're toxic. Oh, I'm the positive.
Actually, you're not positive anymore. You just lost your
Oh yeah,
positivity.
I'm just
You
a
made him
neutral.
positive.
Yeah, I'm just here.
This,
As soon as Yaki gets back.
look, this is dangerous. Dangerous.
You made him dangerous? All right, so do you transfer your cards?
Oh, no, fine.
So, Daniela, who'd you give your card to? Mikhail? So, Daniela, you were the acid. Mikhail, you had to be able to receive that acid, which means you were a you were a base. If you were able to receive that H plus, you're a base, right? It doesn't say here.
Bro, I am
But guess
above
what?
you on the pH scale.
Now who's the acid? Who got that extra H plus now? The base will turn into an acid on the other side. So you carried, but now he's carrying.
Yeah, Sir Leaf wasn't accepting, so she must not have been.
Not a base.
She lost in all directions.
Refuses to accept.
You sold. And I won.
All right, so let's revisit ammonia. Let's revisit ammonia now that we've kind of got this idea. Acids give away, right? And bases receive. Let's revisit ammonia. So I'm going to write it at the top. You'll see it on the next slide, but I want to explain it from scratch. NH3 is the chemical formula for ammonia. What happens when I place NH3 in water? And so that's what I have here. I told you it turned blue. When I had the litmus paper, I have my ammonia. Don't drink it. It's very dangerous, right? Ammonia? Yeah, it's dangerous.
He's worried because
That's
he's
why
very
we're in
someone.
So NH3 plus H2O. Go ahead and put double arrows.
Luke's body right now is like the chemistry.
You know what that means?
It's a reversible reaction.
I'm writing that because NH3 is actually not classified as a strong base, it's classified as a weak base. That'll be later in today's lesson, but let's take a look. So let's talk about the action. We know that ammonia is a base. We proved that it's a base experimentally. So theoretically, what does this say that NH3, go ahead, Dariel's next. What does this say that NH3 will do? What is the actual action of a base? What is happening? It's got to accept an H plus. Daniela, because you brought it up, let's do a little bit of a deeper dive into that. What's the Lewis structure for NH3?
Oh my god.
Beautiful. That's NH3. H plus approaches, right? I'll write that at the top here. What makes ammonia able to receive that H plus? I want you to think about it. Ammonia can take on that H plus into itself. Why? That H plus has no electrons. NH3 is not active. Not double lines, but there was something that we did called a dative bond where you would write an arrow, if you recall. Both of the electrons from this nitrogen will grab that hydrogen. So it actually turns out if something has a lone pair of electrons, it could grab that H plus. It can receive that. Yes, from the dots, the two dots. If it has the two dots, it will make a covalent bond. Hey, what is this? If NH3 accepts H plus, water is giving H plus to NH3. What does this become on the other side of the reaction after it's gained the H plus? What is it now? NH3, add an H plus to it. What is it? No, what is this chemical formula? NH what? With what charge? Because it gave that +1, right? So it's NH4 plus. Hey, is that something you were told to memorize back in the day? NH3 is ammonia that I just told you from the beginning of this lesson. Remember what NH4 plus is? I wrote it up here. It's ammonium because it comes from ammonia. That's why.
I thought they were the same thing.
No, they're not. One is the acid form and one is the base form. NH4 plus is the acid form, actually. Just trying to build a few connections. So as NH4 plus is gained the H plus. What happens to water? Water is operating as an acid, meaning its action is it does what? It gives away the H plus. So what is it left with on the other side? What does it become if it's given away an H plus? OH minus, right? Because if you'll recall, water has two components. It's H plus and OH minus. If it gives away its H plus, what's left is the OH minus. And that's your other product. And that's what you'll see on the next slide. I just wanted to create it from scratch so you understand what's going on. In the Bronsted-Lowry theory of acids and bases, your base receives NH plus and your acid gives away NH plus. Now watch what happens. At the end of your reaction, what did you make when you put NH3 in water? OH minus. And would that be detected by litmus paper? It would. There's the OH minus that's being detected. It's because when NH3 is combined with water, because NH3 is absorbing the H plus from water, OH minus is produced, and it forms a basic solution with a pH graded itself.
Why would it be,
Because the H plus is tied into this. It's not by itself. Like it's covalently bonded into this, so the pH is not sensing H4 plus. It can only sense free H plus, if that makes sense. Kind of make sense? These are all good questions, and it's important that you understand these ideas. Yes, go ahead. All right. Now that I've expanded your brain a little bit in terms of what an acid is and what a base is, this is a repeat of what I I wanted to create it from scratch because I felt like it was better to create it from scratch, but the slide is here. There's something called conjugates. And you might have heard the word conjugate in math class before. I've heard conjugates in both math and science. When you gave away your H plus to someone else, that someone else operated as base, right? But that someone else now has the extra H plus. So that someone else has turned into an acid. And so the acid on the product side is the new acid form. We call that the conjugate acid. So the new acid form, or the acid on the product side, is another way to understand it. We call that the conjugate acid in a chemical reaction. You should write this down, like annotate it. And a conjugate base is the new base form. So when Daniela gave away her H plus, and she no longer has that H plus, instead of being the acid version of herself, she's now the basic version because you lost the H plus. What?
I'm so bad.
So we switch places.
You switch places.
Your basic.
Became the basic version.
I am acidic.
The new
No,
base
you're toxic.
form.
There's a difference. You're the basic or toxic.
Base on
Thanks,
product
dude.
side.
No problem, man. I always.
You want a little drink of?
Don't be toxic.
You were toxic.
Yeah, I pass it on to Dario. He's my
Maybe
successor.
Jose Enrique's gonna gather all those H pluses at the
Yeah.
end.
I'm just basic now.
Yeah, he's gonna be the most toxic person in the room.
No,
The
that's
H
your
pluses
job. I
go.
don't want to take that.
Yes, let's all give him the H pluses after we're done, guys.
I don't want to take his job. I'll just leave it.
You don't want, you said you're not operating as a base, you refuse to accept.
See how toxic I am? I'm just gonna pass it on.
Hot potato. Hot
He's gonna be one of those unstable elements at the bottom of the periodic table.
Nah, man, I'm basic. I'm stable.
Stable base.
Yeah.
All right, so new base form is the base on the product side. The key word for that is conjugate. So on each side of the chemical reaction, there'll be one acid and there'll be one base. The acid and the base on the reactant side are just called acid and base. The acid and the base on the product side are called your conjugate acid and your conjugate base. There's a couple of points I want to make here before moving forward because you're going to have to make decisions shortly. You're going to see what type of questions you're going to solve. The first thing I want to bring up is that on each side of the chemical reaction, there's only going to be one acid and one base. So once you figure out one of them, you figured out the other. The other thing I want to bring up is that whatever compound is a base on one side of the reaction will become an acid on the other. And whatever compound is an acid on one side will become a base on the other. So those are the two ideas I wanted to bring up before moving forward. So on each side, there can only be one acid and one. There is only one acid because one is given away. Your conjugates will always be on the product side. And your conjugates come from the original. So I'll give you a little bit of time to write that down. Then we're going to take a look at a few practice questions. So how will you be assessed? What does your homework look like?
Work.
It looks like work.
No way. Usual office work. Time.
I wouldn't call it what usual office work looks like. Alright, moving forward. In about 20 seconds. On the next slide, I just wanted to show you a conjugate acid-base pair is the acid version of the compound and the base version of the compound, which means the one that has the extra H plus and the one that has lost the H plus. So just to make a little note there. A conjugate acid-base pair is the same compound or substance, just one has the extra H plus, that would be the acid version, The one that's lost to that H plus is the base version. So if HCl is an acid, its conjugate base will always be Cl minus because it lost the H plus and it's left with Cl minus. We call that an acid base pair. And then finally, we're ready to look at some practice questions on this topic. Hopefully the little activity was helpful in terms of helping you understand what's going on here. Take a look at this chemical reaction. Determine what is the acid, what is the base, what is the conjugate acid, and what is the conjugate base. So take a look at this. Can we figure out, let's start with what is the acid. What is the acid here? Why? No. Acids don't.
Then is the base. OH minus would be the base.
Why?
No,
I got it.
HF.
HF is the
Because it has
acid. So not because it has an H necessarily, OH minus also has an H. Look at what's happening.
it has a
Yeah.
positive.
Somebody's out right now when they come back. It does have a break it down, it's O2 minus with H plus 1 equals OH minus. Because negative 2 plus 1 is negative 1. But this is the idea. HF is giving NH plus to OH minus. So it's giving H plus from the HF to the OH minus. You have to see what's happening. HF is becoming F minus. That means that HF had to have given away an H plus, which means that HF is your acid. Does that make sense? Because HF had to give H plus to become F minus. That's how the transfer works. So HF is the acid, which means OH minus is operating as a what? Just a base, because it's on the reactive side. I said the word base in rotation. OH minus is your base. Yes? Because it receives H plus from HF. Now your conjugates are the new acid that forms and the new base that forms. I think it's easier to figure out what's the new base that forms. What's the new base? On the peroxide, what can't possibly be an acid? Think about it.
H2O.
The H2O.
Water can't possibly be an acid. When water is very much defined as having H plus and OH minus.
Oh, yeah. Acid. Wait.
What can't possibly be an acid? Let's think about the definition. Acids give away
H plus.
H plus. Which of these two things does not have H plus to give away? Think about it. Minus, right? That doesn't have H plus. It can't be an acid, even though it wanted to be an acid and don't have the H plus. Right now, if Sarah wanted to give away her H plus, she couldn't do it. Right? She don't have it.
She doesn't
Not anymore. It's all F minus, right? Are we good with that? That kind of makes sense. Doesn't have H plus. It can't be an acid.
Yeah. Having good one.
F minus is your conjugate. Well, once you figured out the base, you can automatically figure out the acid.
Yeah.
H2O.
Water. And you're like, wait a second, miss. I thought water was neutral.
Yeah, wait a second. Is there two depending on water neutral?
But think about it. Water can receive H plus. And when it does, it becomes H3O plus. We said that earlier, right? Water can give away H plus, and what does it become? It has the ability to gain H plus, and it has the ability to give away H plus. What does water become when it gives away its H plus? We did it earlier. Water can operate as an acid or a base, depending on what it's combined with. So water, very special. Thankfully for oxygen, we have water, and then we all live on this planet because of that. Water acts as both acid and base. So to answer your question, it is not that it's neither acid nor base, it's that it could be either acid or base, depending on what it's combined with. It has the ability to give away H+, and because of the structure of water, having that lone pair of electrons, it has the ability to receive an H+ into its structure.
So that's why if you add like minerals and stuff, the minerals will take the hydrogen, which will do a lot.
Which will change the pH of the water. Absolutely. And yet another reason why water is special. You should probably write this down. I'll give you some time. And we'll take a look at the second example. Then we'll have one more topic we need to cover today before we're done. But you all have brought up some fascinating deep dives. You made it the best of the 3 classes so far, and it's for the one that's being recorded, so great job. Unfortunately, the first class didn't have a chance because they had the evacuation yesterday, so they got like a whole abbreviated version of the lesson.
Yeah, recording. Did you stated that we are the best class?
Yeah.
Wow.
Low future.
Ready for the second practice question? You'll see some writing, so I'll pause a little bit longer.
There's like incredible footage of like people in the 1930s building the Empire State Building, and the workers just wave at the camera as they like are building.
Yeah, and they're all dead, so you're just seeing dead men waving.
Oh, but it's kind of cool.
That is cool. That reminds me of going back to New York this summer.
I don't know. I think I'm going to with my friend.
But
We're
it's
going
a
over
crystal
to Life
Cake
World.
Factory.
I went, this is gonna be like probably my third time. Second time.
If
No,
you-
actually, there's one.
I've been to New York
Oh my God,
so
what
many
is it?
times in the last
Imagine
I'm
You
familiar
should.
with people, who knows?
at the top of the
Like one time square, like, is that it?
Could be, depends on the day. Practice question 2. Here we go. See if you can figure out this one. I walked you through the process. Can you figure out here? And I mean, context can kind of give it to you. You're putting water together with nitric acid.
Come on.
What do you think is going to be the acid here?
HNO.
It's God.
Yes,
It can't be the acid.
man, water's gonna kill me. Man.
Which one's more acidic, water or nitric acid?
HNO3.
I don't know.
If
I
you
don't
put
know
nitric
what's
acid
more
in the product,
what's more deadly, water
this is,
or
looks
something
like what's
burns?
happening, right?
Yeah. Yeah.
Water.
Gives H+.
But
So HNO3 is transferring its H+ to water. Water can receive that H+. So what's my acid here?
Water on its own.
the HNO3,
And my base?
the H2O.
On my product side, what's my new acid?
The NO3. Oh no, the H2O. Oh, I'm stupid.
No, you're not.
I forgot the hydrogen stuff.
H3O+ is your new acid, right? And NO3- is your new? Your conjugate. Now, I said something earlier that I told you I'd explain a little bit later. I said that when you place an acid in water, the acid always transfers to the water. Remember I said that? I said at the beginning that H+ that we've been measuring is the same thing as H3O+ because the acid always transfers to the water. That's being shown to you right here, actually. When nitric acid is placed in water, it transfers its H+ to the water. So this is actually the molecule that's being detected, the ion that's being detected as H+. It's actually H3O+ that's being detected in your water. The amount of H3O+ is your molarity of your acid. We say H+ to make it simpler, but it is actually H3O+ that's being detected by like your pH meter. Because all the acid always gets transferred into the water. All right, we got one more thing to cover. This is the math thing. Ready for the math thing? If we have a strong acid or a strong base, how can we determine the pH of that solution? So we're going to go back to pH calculations real quick as opposed to today. Before we do that real quick though, I want to bring up, Cambridge wants you to memorize 3 strong acids. Only 3. There's more than that exists,
It can be any.
but no, it cannot be any. They will be specifically labeled on bottles in your if you take a paper 3. And they want you to know that these 3 are strong acids. They are specifically H2SO4, HNO3, and HCl. 3 of the first 5 I told you to memorize. It's why? It's because they're strong acids. What does that mean? Strong acid. Take a look at what is being said here. Strong acids break apart 100% of their H+. Meaning if I take a strong acid and place it in water, 100% of H+ will transfer into the water. That's why we call it strong. Because it gives off all of its H+. It donates it all the way. So what's a weak acid? What's the difference? Look at the bottom. What is the key difference in what's going on with a strong acid versus what's going on with a weak acid? What does double arrows mean? This reaction occurs and you have a weak acid, some of its H+ is transferring into water, but some of it's staying combined together. Not all of the H+ is transferring into water. And as a rule of thumb, it's less than 10% that's transferring into water. So it's a weak acid because it's only transferring some of its H+, a small amount of its H+. So these are your edible acids, like citric acid, like what's in your lemonade, your orange juice, right? Those are your edible acids. Are not all of your weak acids, but most of your weak acids are the ones that you could eat or drink and have. Whereas strong acids, if you see a labeled bottle of HCl, you would never want to drink that, right? It would corrode your esophagus on the way down. And at very minimum, you'll suffer from ulcers the rest of your life, most likely. Yeah. You know what ulcers? It's like lesions. Because it corrodes. It causes lesions, like permanent lesions on
Could
you.
you die?
You
Could.
should try that.
Depends on the concentration. So you would never drink a strong acid, right?
I don't like
So,
how you said.
How can we determine the strength of a compound that is an acid? Unfortunately, you are going to have to memorize the 3 strong acids. And they are the 3 I've been talking about. Sulfuric acid, nitric acid, and hydrochloric acid. You have to assume that all of these break apart their H+ completely. There are other ones that exist, but they're outside of the Cambridge syllabus, so I'm not going to ask you to memorize anything that Cambridge doesn't ask you to memorize. So those are the only 3 that you need to know by heart. Strong bases. I do want to also bring up before we do the calculations. So real quick before we do the calculations, strong bases are the same idea. And there's an easy way to tell, unlike the acids, there's an easy way to tell you have a guaranteed strong base. Guaranteed strong bases. They are actually all located in the same area of the periodic table. Which area do you think they're at? Your guaranteed strong bases. What's one that you know from the lab that was the highest pH?
Why is there a low M?
It was sodium hydroxide. It is the group 1 hydroxide. Meaning that if you put any group 1 metal with OH minus, it will always dissociate 100%. So if I want to do a lab and I want to make sure that I have all my bases that are transferring into water for you next week in your titrations lab, guess what I'm going to do? I'm going to pick a group 1A metal with an OH minus. I don't have that.
But where's the M? The lone M.
N is metal,
Oh, it's just metal.
and +1 means group 1, right? That's what that's indicating. So all your guaranteed strong bases are from group 1. That's an easy way to remember it. So I typically, like the cheapest one is NaOH, so that's why you'll see it most often. And it's also the one that Cambridge typically tests, but I could swap it for LiOH or KOH or another one, if we have the stock and supply of that. And it would be a replacement. So this leads us to the last thing we're gonna learn today. If we have a strong acid or a strong base, we can directly calculate the pH using the concentration. And I know that I've given you a few questions in the Bellworth last class, and some of you picked up on it and some of you got confused. And it's okay because I hadn't directly taught it yet. But now I am. I'm giving you 3.42 times 10 to the negative third molarity HCl. And I want to know what's the pH of that solution. What's the first thing you have to recognize? HCl is a strong acid. And when it breaks apart in water, how does it break apart? There's something really important here. When you were asked to calculate pH, what was that formula? pH equals negative log of the molarity of H plus, right? Well, this doesn't say molarity H plus, it says molarity HCl. What do we do? Would you agree that this is a monoprotic acid? Every one of this HCl produces one H plus. Would it follow that the molarity is the same? If this is 3.42 times 10 to the negative 3 moles per liter, then this is also 3.42 times 10 to the negative 3 moles per liter. Because it's a 1-to-1 molar ratio. Does that make sense? You should not have to do complicated math, hopefully, to figure it out. You would just take pH equals negative log to the what? Same thing?
Yeah.
Because one HCl has one H plus, so the molarities will be the same. So the negative log of 3.42 times 10 to the negative 3. Put that in your calculator real quick. Let's see what we get. Well, this is our last slide for today. We're going to do we're going to revisit neutralization when we talk about the reactions of the class today. I get 2.47. Let me know if you get the same. How would we do the next one? I've got 0.0042 molarity NaOH. I want to know, what's the pH? What's the first thing to understand here? Is that an acid or a base? I don't know about you, but I see a base. That's hydroxide, right? That's a group 1 hydroxide. That's a strong base. We just said that those were strong bases, right? So can we find the pH directly? Yes or no? What will we have to find first? The pOH is the negative log of the OH minus. Now this is going to be that 0.0042. Because again, it's a 1-to-1 ratio. Every one NaOH, no more bathroom breaks. Every one NaOH is one OH minus. So then the pOH would be what? Log of .38. Is this our final answer? What do we got to do now? 14 minus the pOH is going to give you the 14 minus the pOH gives you the pH. That's going to be 6.2, which should make sense. It's a base. It should have a high pH, not a low pH. And the last one. What's going on with that? Why did I choose that question? What's different about example C? It has 2H plus. So if you were to explain the dissociation, it would look like this. Why am I bringing this up? Because when I take the pH, I'm taking the negative log of the amount of H plus, not the negative log of the compound. So what is the molarity of H plus here? If H2SO4 is 13, what's this? It would be 13 times 2. If that makes sense. All you gotta do is take this and multiply, because you've got double the amount of H plus. It would be 13 times 2, which is 26. So if you understand that, you've got the idea. Negative. If it's diprotic, you would have to multiply by 2. And if it was triprotic and it was strong, you would have to multiply by 3. So negative log of 26. And that would be very, very, very low. Not drinkable.
Are you sure?
Death.
Certain death.
It is certain death.
Only one time.
Oh, certain death.
Like, Miss Lee, everything is physical.
Certain death. All right. So that's it. We are done with today's lesson. I'm going to pass out the homework real quick. I'm just hitting stop on record. Don't get up quite yet until I pass out the homework.